Here's a second case study. It is about data-driven cause finding. In the conventional approach, a clinician would work with a data dictionary to identify the variables that he needs for his study. In our approach, in a data-driven approach, we're going to use machine learning as a tool, and it will rely on the existing healthcare records as well as a data dictionary. Using these two components will help to enhance the clinician's experience in identifying clinical codes. By data-driven, we mean that we're going to complement the existing ontology approach with plenty of anonymized patient records. The approach goes something like this. First, we identify a very simple code, say C10E for type 1 diabetes. Now, suppose we choose a classification task. Patients with type 1 diabetes are labeled as positive, whereas those with type 2 diabetes are labeled as negative. So we can choose an algorithm that selects features whilst doing classification at the same time. The algorithm will return us some features that are relevant to distinguish type 1 from type 2 diabetes. We then, after training, we return the features to the clinicians. If they are happy with the codes, then we will take these codes as they are. Otherwise, the clinicians will refine the codes and then select more instances, more samples, more training samples, or different sets of uh, variables, and let the system choose the relevant ones. The process then iterate several times until the clinician is happy with the codes that he has. There are a number of advantages of using a data-driven approach. Firstly is what I call relevance. Only clinical codes that are actually used will be included in the final list of selected features. The output of the approach is actually a statistical model, hence it can give confidence in terms of posterior probability. Third, because as the system receives feedback from the clinicians, it will get better and better with each iteration. Fourth, there is a tight integration between codes identified and the case finding. Here the case are the patients, so we will know that the codes will be relevant and they can be used to distinguish patients. Finally, because the output is a statistical model, we can use the output to detect potential errors or mislabeling in the data. Let's take a real case study of distinguishing type 1 from type 2 diabetes. I took a subset of the QI-CKD database of 10,000 patients. Out of that, I identified about 500 of the patients have type 1 diabetes using the C10E code. And using another code, C10F, I identified patients with type 2 diabetes. So patients with type 1 diabetes will be labeled as positive examples. Those with type 2 will be labeled as negative examples. We are left with a subset of data where patients are labeled both with type 1 and type 2 diabetes. We're not sure whether these patients actually have two types of diabetes at the same time, or this may be because of mislabeling. As a consequence, we excluded from the training data set. However, we could use the label. We can build a classifier trained with positive and negative examples here, and then use it to test on the excluded data set to find out if actually these patients have both type 1 and type 2 diabetes, to check if this could be an error. Let's take a look at the data and see how they look like. I represent the data as a big matrix. In the row, you have the number of patients, the patient index. In the column, you have the COTS index. There are 11,996 unique COTS here, but I'll show you only the first 1,682 of them, which are densest. By dense COT, I mean that they are very well populated. You can see that the first few variables are extremely well populated with data, But quickly after 200 or so variables, the density goes down rapidly. The figure below shows the density or histogram of how well the data are populated. If I calculate the sparsity of the data, about 98% of the data are empty. Therefore, the matrix is very sparse. Next, I train a classifier to classify the data I've shown you just now in the 11,000 dimensions using regularized logistic regression. Initially, I used logistic regression, but the large dimension of the data causes logistic regression to converge in a U manner. Basically, logistic regression just complains that it can't cope with the variables. So we use a regularized version, and in this version, it has an parameter called lambda, and the idea is to adjust the lambda parameter so that we can choose the relevant degree of freedom of the logistic regression. As the variable lambda goes towards very small number, we see that many more coefficients will be chosen. Now here in this diagram, you see that on the right diagram, you see that the coefficients, the values increases as we decreases the lambda value. Now too small a lambda value will cause the coefficients to grow very quickly, and eventually all the coefficients will take on some values. On the left-hand side, you see how the cross-validated classification error. Here in this case, it's called deviance. Uh, this is a term used by generalized linear model to give us how confident, how well the model fits the data. The lower it is, in general, the better the result it is. It's a bit like classification error. So it is in fact proportional to the classification error. We see that uh, lambda value between 10 to the power about -2 and 10 to the power -3 attains some very optimal results. And here we will choose weights this lambda and use the corresponding model. After training the logistic regression, we use it to test the original the training data set. So in fact, we are applying the trained model on the training data set. What we see here is that for the positive samples, on the left-hand side, I would expect to see high posterior probability for positive samples. But instead, what I have found is that some of the positive samples have actually very low probability. So that means the classifier, although it has been trained with the positive sample labeled positive samples, it complains that I couldn't fit some of these data. So it could be the case that the model is incorrect, or most likely that the training samples, positive samples, might have been mislabeled. So these are in fact potentially negative samples. Now let's look at the negative samples. Again, on the right hand side, we see that the posterior probability are mostly zero for most of the samples, except that there is a small fraction of the samples, negative samples, um, attain very high posterior probabilities. So our logistic regression model seems to suggest that these samples are in fact not negative samples, but potentially mislabeled samples, which are in fact positive samples. So what I do is to create a threshold for rejecting the training samples. So any threshold, any posterior probability below this line, we need to be careful. Um, by this, what I mean is that we'll take, by examination threshold 0.2, for type 1 diabetes patients, we'll take any uh, training samples that attain high posterior probabilities to be positive samples, and very low samples with very low negative samples with very low posterior probabilities to be negative, to be the ground truth negative samples. So we're left with effectively two subsets of training data. Uh, Here for the positive samples and there for the negative samples, and we will only use these to train the next version of the classifier.